6.9, enthalpy of formation, delta HF, and standard enthalpies of formation, it says. Standard, yeah, standard should have mentioned. Worksheet to number 1, A and B, number 3, and now 44. I know in one lesson I was going to try and do that earlier in the last lesson, but I decided, nah, I'll just put it where it belongs. I was trying to get you ahead. But as a result, your Hess's Law lesson was shorter, but that's good because you had some very long ones lately, so it's good to have a short one too. Okay. This is really, this is a pretty easy thing. You're going to really be happy about this. It looks crazy when you see this and you show your friends and your family, oh, here's my homework, look what I did. You're going to be like, what in the world? But the truth is, it's really easy. This and most of what remains in thermochemistry is nothing but bookkeeping, accounting. It's like, imagine you're doing your taxes, or you might not know what that is like yet, or your parents do them, or an accountant does them. And instead they look and say, oh, okay, your income, how many people are in your family. It's all these charts you look through, and how much you have to pay for this and that, and you know, money you give to charities, or how much money did you make, how much money did they take out from the, you know, it's all these numbers and charts you deal with. Well, that's what this is. In fact, I'm not going to hold it in front of you because I did not print it myself. But in the notes I gave you, in the very end of it, if you go all the way to the end, there's a packet that has thermodynamic data. And you need to know this is very important. You need to have that with you. Now, when I give you quizzes and tests, I'm going to give you the information you need. But sometimes we give you a chart. But when you're doing the homework and you're doing the worksheets, you might think, well, how am I going to find, how am I going to find delta HF for CO2? Or for H2O? Or for, I don't know, CCl4? Well, there's a chart. Now, they're not going to be written in that order. But there's a chart in the back of your book. It's actually written the other way around. Like, you might look up a chemical like, say, CO or CO2. It might have CO2 gas, CO2 liquid. I'm just going to make up something. CO2 solid, we'll say. And then maybe CO is before it. And then above it, on the last page, you're going to see this delta HF, delta S. Oh, not delta S. You'll see S. And you'll see delta GF. And you're like, what are these numbers? I'm going to be explaining that in the next lessons. But what you should know is when you do your homework, if it says look in the appendix, your book says that, or if you have to find a value for this, CO2 solid, you look on the chart, delta H, go all the way down, and then there's a number, and there'll be some number written there for you. Okay. It's like the next page, negative 46 for NH3 gas. NH3 gas, it'll say negative 46. And that's kilojoule per mole. You'll know the unit. It will tell you that as well. Okay, why do I need these weird accounting numbers? Okay, so let me talk about that now. In fact, maybe I should just do that problem. Maybe I should do the problem first, the math problems first, and then tell you about the equations. Maybe I'll do that. Maybe I'll flip it around this time. Well, I'll tell you this. Okay, what in the world is meant by standard enthalpy? First of all, let's try to remember what do we mean by enthalpy, delta H. What exactly is delta H? I talked about it a little bit in whatever practical terms is heat, the amount of heat that's released or absorbed during a reaction. If it's negative 300, that means 300 kilojoules of heat were released. Positive 300 kilojoules had to be absorbed or had to be added in order to make this reaction occur. Every chemical reaction has a delta H value. Now, when you're doing an experiment and you use a calorimeter, remember Q equals MC delta T. Well, Q tells you the heat in your experiment that either was released or absorbed. Okay? Well, delta H is how we adapt that into stoichiometry and make it useful for everybody. Okay? So, another way to think of it is to say delta H is the amount of heat released according when certain, how would you say this? The amount of heat released when certain lab conditions are met. Under standard thermolab conditions. Yeah. The amount of heat that's released for a chemical reaction based on stoichiometry under all of these standard conditions. Actually, I need to tell you that right off. 6, 9 right here. Here are the standard conditions. Number 1, it's assumed that standard pressure for a gas will always be 1 atmosphere. So any gases involved in this chemical reaction, if I write a chemical reaction of hydrogen gas, reaction with oxygen to produce water, liquid water, first of all, the gases have to be at standard pressure to get the delta H value. Okay? The standard molarity, it says concentration, should be 1 molar. We won't see that too much in this chapter. 3, for a pure substance in the condensed state, if it's a liquid or a solid, we're saying the standard state will be the pure liquid or the solid. I need to say a little something about that. Yeah, I need to tell you a little something about that right now. And I've told you this already, believe it or not. For every element, what is the standard state? The standard state. Okay, so if you look on the chart, on my chart, everything has the same color, but on other charts, they're color-coded. Well, everything is a solid. Every metal, pretty much everything is a solid. Oh, I don't have my old chart that shows you that little ladder line, except when you get over to this side right here. All of these are at room temperature. At room temperature, all of these, almost every element is a solid, every metal. The noble gases, obviously, they're gases. Hofbrinkel, you should be aware of this. I've told you before. H2 is a gas. O2 is a gas. Nitrogen's a gas. Chlorine's a gas. Everything is except, and fluorine, except for bromine, Br2, and I2. Br2, you need to know, is a liquid. And I2 is a solid. One more element is also a liquid at room temperature, a metal. And which one is that? Mercury. Mercury, just know that that one is also a liquid. If I have iodine, it's a solid. Okay, and so the gases, I've told you, hydrogen, oxygen, everybody in Hofbrinkel is a gas. Everybody in Hofbrinkel is a gas, except for bromine and iodine. All the other nonmetals are solids. So everything on the chart is a solid. Assume that. Now, yeah, assume that, except group 18 are gases, and we're not going to see those a whole lot. And then everything in Hofbrinkel is a gas, except for bromine being a liquid, iodine being a solid. And I say that they're a solid at standard pressure and at standard temperature. Now, here's the weird thing in this chapter. Standard temperature, according to physics and to thermo and to all science, is 25 degrees Celsius. That's why I always told you, I don't like standard temperature in the gas law chapter being 0. Okay, so that's why I think AP is not going to ever ask you standard temperature. When they say standard, it'll only be in thermo. Standard is 25. How weird that is. So 25 is pretty much room temperature. So the temperature in the room right now where you are is probably close to 25. Okay, it might be a little bit colder in this colder weather. 25. If you're at 25 exactly and you're at sea level air, 1 atmosphere air pressure, what will O2 be? O2 will be a gas, right? So the periodic table, you should know how to predict what every element will be at room temperature. And just think about it. In the room right now, when I see H2O, is it a solid, liquid, or gas? It's a liquid. Now, you might say, well, what if I get a piece of ice out? If I take out the piece of ice, it is ice right now at room temperature, but you know it's melting, and it will come back in about 2 hours. It will be water, because at room temperature, at 25 in 1 atmosphere, it will be a liquid. It's just it might have to get there from the internal energy in the system and all. Okay, so when all these elements are in their standard state, standard pressure, standard temperature, and all that, then the delta H value is the one you'll see on the table in the back of the book. It matches stoichiometry. So, let me watch how this goes here. All right, so here we go. So the first thing I'm going to do is, I think I'll just go and calculate the equation. The standard equations. I can see them right here. Well, I guess I'll go in order with the equations. Standard enthalpy of formation, and I wrote the official definition. The change in enthalpy that accompanies the formation of 1 mole of a compound with its elements from its elements with all substances in their standard states. All right. Enthalpy of formation are always written. Enthalpy of formation equations are always written to express forming 1 mole of substance. Very, very important. Okay, so I'm going to show you this right now. I'm going to go right to the end, to letter A, and do an equation for you. And you'll like this. Now, this is not like the equations we've been doing on our drill quizzes before. This is different. And this is something that's only used in thermo. And it also, like much of thermo, can be just theoretical, meaning we've never actually done this. But most of these can be done, or a lot of them can be. Number 1 says, write the equation for the delta H formation for solid calcium carbonate. Okay, calcium carbonate is CaCO3. Now, if I want to get a value for delta H of formation, delta H of formation of calcium carbonate. Well, you can put it up here too as well. I was going to put it there. That value will only be true. It's the amount of heat that will be involved when calcium and carbon and oxygen, and you know oxygen is not O but O2, all react to form calcium carbonate. Now, you pretty much never have 3 elements that come together in a reaction. But again, it's just theoretical. What is calcium at room temperature? In the room right now, it will be a solid. What about carbon? It will be a solid. Oxygen, I told you, will be a gas. Calcium carbonate is a solid. Pretty much every ionic compound, if it's a metal and a non-metal, positive, negative ion, or so metal, non-metal, positive, negative, they're going to all be solids at room temperature. Now, we're not talking about aqueous. That would be a different story there, but they all will be solid. So you're not using the solubility rules on this part. All right, now, how would I balance this out? You might say, well, I need to have 3 oxygens here, so I'll put a 2. 2 times 3 is 6. 3 times 2 is 6. 2 calciums here, and I want 2 carbons. So 2 calcium, 2 calcium, 2 carbon, 2 carbon. 6 oxygens. 2 times 3 is 6 oxygens. Now, here, but we still are not there yet. In the correct equation, delta H of formation should be, this has to be 1 mole of calcium carbonate. So how can I turn 2 into 1? Well, I'll have to divide by 2. So I'm going to divide that number by 2 to get 1. But if I divide that by 2, we've got to divide that by 2, and that by 2, and that by 2. And now, as a result, I get carbon solid 1 plus 3 halves O2 gas gives you 1 calcium carbonate solid. And the delta H of formation for calcium carbonate, that is true for that equation. You know, I don't have it with me. Let me see if I can find it, though. You know what? I might not be able to. No, I'll have to look on the chart. Enthalpy. I want the enthalpy of calcium carbonate. I wish I knew the number real quick. It would just help me to have that value, because you could see it on your chart. Oh, here it is. It says negative 1270, but let's see what unit that is. Oh, kilojoule per mole. Okay, I found it. Calcium carbonate solid, negative 1207. Negative 1207 kilojoule per mole. So that's what it means for this equation, and this is one you might use in Hess's law. That's why you see these fractions in thermo, because those fractions are there because we have to always make the formation. We have to make it 1 mole of the formation. Okay, so there it is. Now, enthalpy of combustion of C2H6. What will be the equation for that? I'll show you one more example. C2H6 combustion with oxygen will always give you carbon dioxide and water. You should know that. Now, H6, okay? So 2 carbons, 2 there. 3, uh-oh, that's not going to work out good. 3 times 2 is 6, and 6, that works out. Oh, it does work. And on the right you have 7 oxygens, but here you have 2 oxygens. So I would normally say, well, I'll put a 7 there and then double everything. Remember how we did that? Like if I put 3.5 there, times 2 is 7, and then I've got 2, 4, 5, 6, 7 on that side as well. Well, what I'm going to have to do, though, then I'll have to double everything. I'd say, okay, well, now I'll double that to 2. That will become 7. That will become 4. And that will become 6. But now, they want you to find that delta H of combustion. Now, there's something about that word combustion. All this really means is you're finding the delta H of reaction. So I'm just going to let you know, this, you could just use the word reaction there. In fact, I might put RX in. That's what you're going to see a lot on AP. But if you see below that, instead of RXN, if you see COMB, combustion, combustion just means it was a combustion reaction. But it's really, reaction is the more general term that you can use for all of it. All right, instead of that, you might see combustion. You might see neutralization. Whatever. Like if it's an acid and a base, it's a delta H neutralization for that reaction. I think we did that on with the calorimetry problem. So, but still, you can call it delta H of reaction. Combustion, neutralization. It could be synthesis, decomposition, delta H of decomposition. You can put any type that you want to, but reaction is probably the more general one. But anyway, it said what will be the reaction for delta H combustion of that one, the equation you'd write. Now, since it says combustion, we'll make it 1 mole of the C2H6. So now we'll go back to where we were again. We'll divide everything by 2 to get 1 there. And what do you know? I'm going to go right back to where I was. Divide by 2. So that becomes 1 mole of C2H6 plus 7 halves, or 3.5 O2, plus 2 CO2s, plus 3 H2O. And now the value that you see for delta H of reaction would be that exactly. Would be for 1 mole of C2H6. So really, the more important thing is to know that formation means to form 1 mole of something. If I want to combust ethane, it says here, is to combust 1 mole of ethane. So there's some problems like that you'll see on your worksheets to do those. All right, and I might have to continue the math part right after this. Or you know what, I've almost got it. Maybe I'm just going to try to jump through and finish it here, even though I've got a lot of things going on. Where did I put? Oh, there it is. All right, so yeah, I'll do it. I think I'll do it just about 5 minutes here. So for B, the standard enthalpy change for a reaction occurs. Calculate the standard enthalpy change that occurs when ammonia is burned in air to produce nitrogen dioxide and water. Now, this is the way they put them on the AP, and you'll see it on my quizzes this way. But in your textbook, you might not see it this way. You might have to look in the back of the notes packet to find the values for all these things. But here's the reaction. 4 ammonia gas plus 7 oxygen gas gives you 4 nitrogen dioxide gas. NO2, by the way, is a reddish-brown gas. Really cool thing to know. Okay, and you also get 6 H2O, and it's a liquid. And they want you to find what is delta H for that, the standard. I'm sure they want the standard, yeah. Standard delta H for that reaction. Sometimes it's right, delta H. Oh, sometimes you see delta H. The degree sign means under standard conditions. That means 25 Celsius, 1 atmosphere pressure. All solutions are at 1 molar. All gas pressures are at 1 atmosphere. And when those react that way, this is what the delta H of reaction would be. You can also call this, there was something I was remembering to tell you, but I forgot now. Oh well. Sometimes you might see this. You might see RXN, or you might not see that. Okay? Or you might also see 298 sometimes written down there in really older textbooks. 298 means 25 Celsius. It means standard temperature, standard conditions is another way to do it. But now they pretty much always write reaction. It looks like now they're always doing RXN. That will be standard. Now, if you ever see that there's not a standard up there, then that means maybe one thing, even if one thing were different from the normal lab conditions, like, oh, maybe we weren't at atmospheric pressure. It's 1 atmospheric pressure. Well, then you can't call it standard. But to get the standard value, you have to do all the things we told you. All right. Okay, so here we go. Calculate delta H. Well, here's the equation that is used. It actually comes on the page before it. And what a bizarre looking equation this is. It says, I'll write it up here, delta H is equal to, now that should not be, delta H, it should be RXN. I wrote that wrong on the note page. Is equal to the sum of the delta H of formation standard of the products minus delta H of formation of the reactants. Now, there's a little change that I'd like you to make on this. Well, that change was a typo. That should say RXN, not F. But here, I like to add the letter N in front of that, and N, which stands for moles. And you'll see why in a moment. All right. It's always the products minus the reactants. The sum of the products minus the sum of the reactants, actually. Another thing that I like to always add in, well, you don't have to write the equation up here, is to always put brackets around everything because you're subtracting something. And you know, when you minus a negative, it becomes positive. Or when you minus a positive, it's negative. So that's an important thing to know. Then, what you would normally do to find this, I've got to look up on the back of my chart, and you can do that if you wanted to. What is the delta H of F formation value for H2O liquid, for NO2 gas, for O2 gas, and for NH3 gas? And if I look on my paper, I will find that right here. Okay, so here they are written on right there by the papers. One is not there, and I'm going to tell you why in a minute, and I'm going to tell you what it is. So listen carefully. I'm going to tell you something very important. Very important. So I'm going to make an equation. It's always products minus reactants. So for my products, I'm going to start off with 6 H2O. No, 4 NO2, sorry. 4 times the delta H of formation of NO2 standard. That's the first thing I'm going to do. 4 times NO2 standard plus 6 times the delta H of formation standard of water. Now I'm going to put brackets around that as well. Okay? Like the chalk. I'm then going to say minus 4 times the delta H of formation of NH3 plus 7 times the delta H of formation of O2, oxygen. All of that will give me the delta H of reaction. All right, so let me plug the numbers in. What is NO2? Now, you got to be very careful. NO2 gas. You have to look for gas. A lot of times, they're going to give you NO2 gas and solid and liquid all there, and you don't need all that information. You only need NO2 gas. For NO2 gas, it is 34 positive. So 4 times positive 34, and these are all kilojoule per mole. That's the unit. I'm not going to add them into this right now, but they should all be in the same units, okay? I'll talk about them in others. 6 times delta H of formation of H2O liquid is negative 286. Minus 4 times the delta H of formation of NH3 gas is negative 46. And then you might say, well, wait a minute. They didn't put O2 on there, and they love to do that. Here's the why. For any very important rule, I should have said it. It might be in the notes in there too, but you wouldn't have understood it till now. For every element, every single element in its standard, if it's in its standard state, the formation is 0. Isn't that fun? You get to put a 0 in there. So what that means is for O2 gas, it's 0. Now for O2 liquid or O2 solid, there'll be a value there for you. Okay? If you're doing carbon dioxide, oh, no, I'm sorry, it's not an element, not an element. If you're doing like iron, Fe, what is iron at room temperature? Is it solid, liquid, or gas? Iron solid would be, iron will be solid, which means, okay, I'll say it backward. It'll be iron will be solid, okay. At room temperature, metal would be a solid. So that means 0 would be its delta H of formation for iron solid. Now, if you have iron liquid or iron gas, then there'll be a number there for you. So anything in its standard state is 0. So now we just have to do the math for this. And what you do is, let's say 4 times 34, 136. Now watch how I'm careful. I try to be so careful with this. 6 times negative 286 is negative, so that could be a negative 1716. I'll make it negative. A lot of times I'll just, well, oh well. 4 times 34, 136. 6 times 286, negative 1716. Minus 4 times negative 46 is negative 184. Plus 0 equals my delta H of reaction, standard. Sorry, I put my standards there. Okay, so 136 minus 1716 is negative 1580. All right? Minus negative 184. Look at all the minus negative parentheses. That's why it's good to put brackets around this stuff so you don't mess it up. And then 1580 negative, minus a negative means plus 184. So it's negative 1396. Now with sig figs, oh yes, there are sig figs too. Actually, in this one there could have been a dot there, 136 minus that. But I didn't put the 2. Well, no, it wouldn't have been needed. Yeah, you could have put 2 sig figs into this one. I'm not gonna go too crazy with the sig figs on this, but looks like it would be more like 1400, but 13. I'm just gonna put the answer straight through, 1396. Kilojoule per mole. Always put a unit, especially in the thermo chapter. You might not know that thermo is a chapter that they love on AP. They love to grade the units on thermo in this chapter. Okay. I'm not going to do one more problem for you. I don't have any more in there. But I want to tell you something about one you're going to see on your homework. Because you are all so good with your algebra, I hope, that you can do this without me telling you. But I'm going to tell you how it works. You can do it on your own if you want to try it. But negative 1396 is the delta H of reaction. Sometimes they give you a problem, just like another problem type, and they'll say, hey, for this reaction, negative 1396 kilojoule per mole is the answer. Tell me, find delta H of formation of, we'll just say NO2. Find it. And on the chart, when they give you all those numbers, NO2, it says, is 34. They won't give you 34. It'll just be blank. It'll be a question mark there. Well, how would you do that? Well, then what you do is you go all the way back and you do algebra here. And you say, well, let's just say they did not tell me NO2, whether it was the first one. They didn't tell me what that was. So instead of putting a number there, I'm going to put delta H NO2. That's like my X. I'm going to solve for delta H of formation, of F of NO2. 4 times the delta H of formation plus 6 times this is still going to be true, but your answer is negative 1396. So basically it's just saying, can you solve this and find, let this be X. Solve for X in that equation. If you know this, that's the other kind of way they like to do this on the AP. So either they have you find it, or they ask you to solve for X. When we do the class, the online and Zoom, maybe I'll do one like that for you to show you. But anyway, that's everything. Standard enthalpy of formation. Wow. But it's not that bad, is it? It's not too hard. All right, I'll see you guys.